Okay, everyone, here we are with the second video lecture for Chapter 17. We're going to wrap up Chapter 17 now with this video lecture. This is going to be a fairly short one. So now we're going to talk about a variation on the one sample t-test that we talked about in the first part of this video lecture. Remember, in the case of a one sample t-test, what we're doing is taking a sample, calculating the average for that, and using that average as an estimate of the true population mean that we don't know. But in addition, and specifically with the t-test, we're going to use the standard deviation of that sample as an estimate of the population standard deviation. And that second point about standard deviation is why we're using a t-test and not a z-test. Okay, that's a key point. All right, so in a one sample t-test, we're calculating the sample average and using an estimate of the population standard deviation via the sample standard deviation to figure out if that sample mean is far enough away from our hypothesized null mean to be considered significantly different. Okay, so we calculate a t statistic. We find where that t-statistic falls on table C, and from that we can derive a p-value, which allows us to make that determination about significance or not. In other words, accept or reject our null hypothesis. Now we're going to do a variation on the one sample t-test called a matched pairs t-procedure. And in this case, we're looking to compare, the effect of a drug or something like that at the level of the individual. Okay, so data sets here are not independent of one another, and you'll get what I mean here in just a minute. Okay, so the point is that the individuals in our sample, or the individual data points that we use to generate our sample, are related to those in another sample. So we have two data points in particular that are related together, or related to each other in some way. They're not independent. Best example of this is pre and post test scores. So for example, in my Bio 1530 class, I give the students a pre-test at the beginning of the semester, and that tells me what they know coming into the class. We go through the semester, then at the very end of the semester, I give them the exact same exam as a post-test, and so now I have two scores for each student, a pre-test and a post-test score. Those two scores for each student are matched. So for student A, those two scores are matched. They're not independent because they're linked in the sense that they are for the same subject or the same student. Okay. We can do the same thing with, you give somebody, or you take a measure of blood cholesterol levels, let's say, in a person, then give them a drug purported to lower blood cholesterol levels and take a sample of their blood again afterward. So you have a pre and a post drug score, basically, for cholesterol levels. Those two measurements are linked. They're not independent. They're a matched pair. You can do this with twin studies, for example, genetic twins, right, to try and figure out the influence of some genetic factor, for example. Everything else is the same because those two twins are essentially genetic clones of each other. So that's one way to do this. This is a way to sort of try and eliminate variables, right, or variation. You can also, use people that are matched for age, sex, education, and social studies. This is very commonly done in the social sciences, and allows for canceling out the effect of potential lurking variables. But in terms of understanding matched pairs, probably the best way to think about it is in terms of this first example here. Okay. All right, so in these cases where we know we're going to have a matched pairs design or a matched pairs t-test, we're using the pair data to look for a significant difference in two population means. All right, so importantly, the variable that we're looking at is the mean difference or the average difference. So average difference in these 10 students in their pre-test scores versus their post-test scores. So the mean difference is what is the statistic that we're testing. So our null hypothesis is going to be that the mean difference equals 0. So in this case, under the pre and post test sort of example, if the null hypothesis is 0, or the mean difference is 0 for our null hypothesis, that's a way of saying that students didn't learn anything in the class. Their post-test scores are on average no difference than their pre-test scores. The mean difference is 0. The alternative could be that the mean difference is greater than 0, or it could also be less than 0. Both of these cases would be a one-sided test, or a one-sided alternative, or it could be that the mean difference is simply other than 0, different than 0. Could be greater than, could be less than. This would be a two-sided alternative, okay? So this is essentially the same thing as a test for one population mean. It's just that we're looking at the mean difference between two separate measurements of something. So let's look at an example. This is actually the example we looked at in the earlier part of this chapter with the 53 obese kids aged 9 to 12 who were put on the stoplight diet to see if it had any effect on weight change. And so the assessment here is weight change again at 15 weeks of intervention. Well, there are two measurements of weight for each of these children, one before starting the diet and one after. And you can see each of their individual weight changes. So for example, this first number of 16.7, that is that person's weight change from beginning to end. So they had a weight measurement before, weight measurement after, that person lost 16.7 pounds. So you see we have weight measurements or weight changes for all 53. If we average all of these, we get the mean difference. And that is the statistic that we're testing here, okay? So this is a pre and post test, post design, right? And it's a matched pairs, okay? Because there are two measurements that go into each of these, a before and an after weight. All right. Another example of this question, does lack of caffeine increase depression? Randomly selected caffeine-dependent individuals were deprived of all caffeine-rich foods and assigned to receive daily pills. At one time, the pills contained caffeine. Another time, they were a placebo, a sugar pill, for example. Depression was assessed quantitatively, so using some probably sociological or psychological survey or something like that, but higher scores represent greater depression. Okay, so you see we have our subjects here, 1 through 11. We have their depression score with caffeine and depression score when they were taken off caffeine. And we have the difference. So 16 minus 5 gives you 11, 23 minus 5 gives you 18, and so on. So these are the difference scores. We average these to get the mean difference, okay? It's a matched pairs design because each of these values represent matched pairs. And again, we're looking at the difference values in terms of mean difference, okay? All right. So we have a total sample size here of 11. We have 11 difference points. That means our degrees of freedom is n minus 1 or 10. And again, this is going to tell us what row of our table C to look at. So we find our mean difference equals 7.36. Take all 11 difference points, average them, you get 7.36. The standard deviation is 6.92 of those 11 points. So remember, we have to calculate our denominator here, which in the case of calculating t, well, let me fill this in, okay? Sorry, this is writing so thick. I'm not sure why that is. I need to check on that. Anyway, let me fill this in because for some reason it never translates, okay? All right, so we've got to calculate the standard error of the mean, which is our denominator here, right? And that is the standard deviation of your sample divided by the square root of the sample size. So it's 6.92 divided by 11, 6.92 divided by 11. That's going to give us the standard error of the mean. Works out to be 2.086. You see it right there. Then the numerator is going to be the mean difference minus our hypothesized mean difference. Oops, forgot you there. So hypothesized difference here is 0 under your null hypothesis, right? In this case, there'd be no difference in depression levels whether somebody was on caffeine or not, versus a one-side alternative that there be a that going off caffeine does actually increase depression levels. Okay, so our mean difference score of 7.36 minus 0 gives us 7.36. Divide that by our standard error of our mean, we get a test statistic of 3.53. So right off the bat, that's telling you that this sample mean difference of 7.36 lies approximately 3.5 standard deviations away from our hypothesized null mean of no difference of 0. Right there, you know you're already better than 95% certain that this is a real effect. But let's see how certain. Let's find our p-value. So on table C, we have to look at degrees of freedom of 10, n minus 1, that's the row, go all the way over, and we find our t-statistic falls between 3.169 and 3.581. That corresponds to a one-sided p of 0.0025 to 0.005. Minitab would calculate that more accurately or precisely at 0.0027. So this is highly significant, very significant, right? You can see that right there. So caffeine deprivation then does cause a significant increase in depression. P less than 0.05, sample size of 11. That's a matched pairs design. It's a one sample t-test. We've already done it before. It's just we're specifically looking at the mean difference rather than just a sample mean compared to a hypothesized mean. Here we're doing mean difference compared to a hypothesized mean. Okay, now what about robustness of the t-test? I've said before, t-test is pretty robust, which means that it's not greatly affected by skew or outliers in our population, okay? So the T procedures are exactly correct when the population is exactly normal, but having an exactly or precisely normal population is a rare thing. So given that T procedures are robust, they're widely used. And it's a simple test, which is another reason why it's widely used, and they can be applied to a lot of different situations. So they are robust to small deviations from normality as long as we meet some assumptions here. Okay, first of all, the sample or the data in the sample must have been randomly collected. So we're talking about, blind studies where the participants don't know if they're getting placebo, sugar pill, or the real drug. Maybe a double-blind study where, in addition to them not knowing, the researchers don't know and some third party is keeping track of all that to try and eliminate bias on the part of the researchers. If you're collecting data in a field study, you want to be collecting from all possible areas, not just sort of cherry picking where you collect from and therefore possibly not collecting data from one given area, which might skew your results, okay? Collect your data at random. Second assumption, outliers and skew can strongly influence the mean and therefore the T procedures, but their impact is less and less as sample size increases, again, because of central limit theorem. We've talked about that, right? This is why you select take the largest sample you can. So as far as sample size, what kind of guidelines are we looking at here? Well, if your sample is less than 15, the data must be close to normal and without outliers. Small sample, so you've got to meet these requirements. If your sample is somewhere between, say, 15 and 40, mild skewness might be okay, but outliers are, again, not going to be acceptable. But if you have a sample size greater than 40, the test statistic you calculate, the T statistic, will be valid even if you have strong skewness and maybe mild outliers. So if you don't know what your population looks like, if it's skewed or not, you want to try and get a sample larger than 40, just sort of as a general rule of thumb. Okay, then you don't have to worry about whether it's skewed or not. So let's look at an example. Does oligofructose consumption stimulate calcium absorption? Healthy adolescent males took a pill for 9 days and had their calcium absorption tested on the 9th day. The experiment was repeated 3 weeks later. Subjects received either an oligofructose pill first or a control sugar pill first. The order was randomized and the experiment was double-blind. Okay, so here we have fractional calcium absorption data in percent of intake for 11 subjects. So for example, this first subject, number 1, had on sugar pills 78.4% absorption for calcium. On oligofructose, they only absorbed 62% of their intake of calcium. The difference was 16.4. So you see we have a different score for each of our 11 subjects here, right? Okay, so we're trying to assess normality here. We only have a sample size of 11, so it's small, so you know it's got to be, your data has to be normal. If it's not, then you can't do a t-test on this. So the question is, can we use a T procedure for this study? Well, you want to assess normality. So you can do a dot plot. You could do a stem and leaf plot. Those will tell you, because those are okay for small sample sizes. A histogram is not good here because it's generally going to be for larger sample sizes. A histogram for 11 data points is not going to show you much. probably the best thing to use is the normal quantile plot that you see right here, okay? Now remember, for a normal quantile plot, we're converting all these difference points to t-scores in this case and plotting them against their actual value on the y-axis, and you're looking for a straight line pattern. If you have a straight line like we do here, that tells you your data isn't normally distributed. So in this case, even though you have a small sample of 11, it's normally distributed, so you're good. You can do a t-test on this with not much problem. About another example, red wine in moderation, okay? So does drinking red wine in moderation increase blood polyphenol levels, thus maybe protecting against heart attack? The idea here is that, there's at least some data suggesting that red wine consumption may have some, in moderation, may have some benefits for cardiovascular health. So that's what this is looking at. So 9 randomly selected healthy men were assigned to drink half a bottle of red wine daily for 2 weeks. The percent change in their blood polyphenol levels was assessed. So we have percent changes in blood polyphenol levels right here for each of those 9 subjects. See a mean of 5.5, standard deviation 2.517, degrees of freedom of 8. So we're assessing normality here. So look at the dot plot. What do you see? You see a large gap there between this data point and this one. That's a low outlier. So because that's a low outlier with such a small data set, a sample size of 9, this data is not really acceptable for a t-test. A t-test would not be appropriate here. You just couldn't have enough confidence in the result that you get because that data is skewed due to that outlier. So you could collect more data, and maybe if your data fills in that gap, even if you only have maybe 15 data points, then you could do it. But with that said, if this is real, okay, if that gap there remains, let's say even if you collect a sample size of 40, if it remains, then because your sample is so large, you don't have to worry about it. You could go ahead and do a t-test then with a sample size of 40, even if you had that outlier there. Wouldn't be a problem at that point, okay? All right. So that wraps up chapter 17 on t-test. This was all about a one sample t-test, which included matched pairs design. In the next chapter, we're going to talk about a little more complex t-test, a 2 sample t-test.